weeks, and we'll be busy learning string theory. And I was listening to Mark Weiss's lecture before, and the way we'll do it, we will start sort of slowly, and we'll be seeing strings probably by Wednesday for the first time. And before that, we'll set up a few of the ideas we need to know in order that we have the language and the technology and a conceptual preparation to the key elements that will be necessary later on. So without further ado, I want to say what we're going to do is we're going to be studying string theory. And the reason people study string theory is essentially falls into two categories. One, it may be a unified quantum theory of all interactions. So that includes gravity, and it's really the reason why string theory became popular in the 80s. Suddenly, we seem to have a theory that could do everything. And of course, that's very difficult, but very interesting as well. If it's supposed to do everything it's supposed to do for you particle physics, the kind of standard model ideas all should come out from string theory and cosmology, because string theory in particular contains gravity. Then another reason people do string theory is because of applications. And the applications run into very many areas, and probably they're all quite interesting. One that perhaps is not too relevant for us, but it's fascinating, is the applications to mathematics. If you look at the various areas in string theory, you cover pretty much all of mathematics, depending what you specialize on. You can cover Riemann surfaces, which are two-dimensional surfaces. You cover Riemannian manifolds, which is the higher dimensional theory of Riemann. You cover number theory. You cover differential geometry. You cover group theory. You cover lattices. You cover everything. It's unbelievable how much there is. And there's rich examples. So it's very interesting. Even as of now, string theory, for example, has suggested generalized ideas here. For example, a branch of mathematics called generalized geometry. It is very popular. It's being done in the Toronto area. Marco Gualtieri, for example, works on that. There's an enormous amount of stuff going on here, and it's quite fascinating. There's certainly application to gravitation and to black holes. There's applications to gauge theory. I'll use this blackboard. Now, you would say application to gauge theory, application to particle physics. It's sort of funny how it works out, because it turned out that string theory was initially most exciting because it could do gravity, quantum gravity, something you could not do before, and do it in a nice, simple way. You used to get infinities. You don't get them anymore. It was just marvelous. But suddenly, what has happened is that in some conditions, some situations, there's string theories that are supposed to be describing gravity can also describe gauge theory. through gravity. So you have a description of gauge theory as a gauge theory, and you have a description of gauge theory as a gravity or as a string theory. And that's the idea of the ADS-CFT correspondence. And that's why it has had many applications to gauge theory, to heavy ion physics, It's the quark-gluon plasma. And nowadays, there's applications to condensed matter physics. And these three, fall under the rubric of the ADS-CFT correspondence. So, enormous amount of applications. For your later courses here at Perimeter this year, I believe you will be told quite a bit about the ADS-CFT correspondence, as it teaches you something about gauge theory. Some courses in string theory are engineered to get you to do this most efficiently. Then you don't have to learn everything about string theory. You can zoom in into some directions that are going to be most useful. Nevertheless, this course that we're going to do is not going to be necessarily in that way. We will talk about these things, but I will teach you some things about string theory that I believe everybody should know, and that they're important whether or not you're going to be focusing in any of these three applications, which are some of the most active areas of research. I would say probably 60% of the string theory community is nowadays working on these things. Small numbers here, and certainly a good number here as well, maybe 20%. And, but this dominates nowadays a lot of what's going on. So what are we going to do? We're going to plan. Our plan is week 1 is classical strings. Week 2, quantum strings. And week 3, applications. And today we start with classical strings. Applications is going to have a little bit of the ADS-CFT correspondence, and basically also some more advanced tools in string theory. You see, to learn some of the basics and the most important ideas of string theory, you don't need all that much, happily. You don't even need to know quantum field theory. The way we're going to do it is we're going to emphasize those ideas about string theory that are really key to what makes a string different from particles. So we will not necessarily have to use very sophisticated tools. But that doesn't mean things are very simple. It's a game with simple rules, but nevertheless can get quite interesting and quite sophisticated. So another remark, perhaps organizational, I'm going to follow and give assignments that are going to be based on the book I wrote on this subject. And the book is available. Debbie Gunther has the book, has many copies of the book. You will probably benefit from having it in order to read and to do the problems or do other exercises if you need more. There's several copies in the library as well, I've been told. And it's going to be used for most of this, except a few things in week 3. Sometimes when if I feel that you guys want something a little more advanced or more sophisticated, I'll just bring it up. But there are many other books that are wonderful in string theory. They're all more advanced and more complicated. And if you will continue in this subject and want to know more, you will probably use them at some stage, as well as review articles and things like that. So I'm about to start. Are there any questions or remarks or suggestions or petitions or anything that you would like me to address at this moment or do? Okay, so I'll get going. I think I figured out how to make these things work. Here. So we're going to talk for a few minutes about relativity and very simple things that you know about. So special relativity. Because what we're going to be doing is really the relativistic string. You see, you probably studied, and we'll review a little in freshman physics or undergraduate work, a string stretched between 2 points vibrating, and that was a classical ordinary string. It had mass per unit length, it had tension. The string is a relativistic string. It's the only difference that we're going to do now is that that string is going to be relativistic. And you would say, well, what's so difficult about making a relativistic string? It's fairly difficult, actually, unless you have the right idea how to formulate the theory of a classical relativistic string. So we're going to, in this week, as we develop these ideas, we're going to be focusing on understanding what is different about a non-relativistic string and a relativistic string. What happens? And the fact is that the relativistic string is much more elegant and much more interesting than the ordinary string. And with an ordinary string, you have it between 2 points, and you release it, and then suddenly, just what does it do? It falls to the ground, does nothing. Relativistic string, if you release it, it keeps going and just keeps moving, and you can keep analyzing what it's doing. It's a very nice thing. So it's all relativity and strings. And in doing the classical stuff, you really discover some of the most interesting properties of the string theory in 2 ways. Let me tell you, there's the string theory, people say, begins with the paper of Goddard, Goldstone, Reddy, and Thorne, which are the first people that demonstrated that you could take a classical relativistic string, quantize it, and you got what was called the dual resonance model. That thing that people call string theory was the quantization of a classical relativistic string. And Professor Goldstone is at MIT, still working there. He's 76 years old. He actually works now in quantum computation. And he was one of the people most involved in this project. And he had spent the whole year before quantizing the string analyzing all kinds of classical string motions of strings until he had an intuition of how this really worked. Moreover, the classical motion of strings is relevant to the motion of cosmic strings. So you also need it for that. Finally, string theory, as you study, say you're going to see the standard model at 3 level. That's the classical sort of processes of the standard model. Einstein's gravity begins as a classical theory. It's a wonderful theory with square root of G, R, Riemann tensors. And in string theory, one should admit, we're lacking the conception of what is a classical field theory of strings that replaces Einstein's gravity. So half of the mysteries that remain in string theory are really classical mysteries and classical field theory mysteries. Yang-Mills theory is replaced in string theory by some Born-Infeld classical theory. Gravity is replaced perhaps with some generalized geometry theory, and they're all classical. So it's not a waste of time to do classical strings. So relativity. Well, we'll use notation in which we have coordinates. There will be more than 4, but let's begin with 4. x1, x2, and x3. And they are ct, x1, x2, and x3. And ct, in order that they all have the same units, an index that runs over 4 values. And the first postulate of special relativity is that there's something called an invariant interval denoted, and my sign conventions are opposite to the ones you got in the previous lecture. It's the mostly space pluses. So we take a minus sign for time and pluses for space. Most string theories do that one. In quantum field theory, half of the books use each of the conventions. But in string theory, I think every book is using this minus, plus, 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 plus. So I will continue with that. So there's this invariant interval that is minus dx0 squared plus dx1 squared plus dx2 squared plus dx3 squared. And being an invariant interval, what it means is that if another observer sees these 2 events, to have an interval, you need 2 events. And there's a difference of x0s, x1s, x2s, and x3 between these 2 events. If another inertial observer sees that same 2 events and computes minus dx prime 0 squared plus dx prime 1 squared plus dx prime 2 squared plus, happily I just stopped with 3, x2 prime 2 prime 3 squared. If you have this thing, you have an equality. That's the fundamental equality. And there we go. And we write this as eta mu dx mu dx nu, and eta mu nu is a matrix that has the first index is the mu, the second index is the nu. It has minus ones, 1, 1, 1, a big 0 here. This is the so-called Minkowski metric. If you run all the indices, here we're using a convention that you're probably quite accustomed. The convention where repeated indices are summed over, so you sum over this thing, so you have 4 values, 4 values. There should be 16 terms here. Those 16 terms must somehow reduce to 4. That's why there's 4 non-zero entries here. And if you run it out, you get eta 0, 0, dx0, dx0 with a minus and all the other ones here. This matrix is equal to the matrix. This should be a definition on this direction, eta mu nu. It's called the inverse matrix, but the inverse matrix of this is the same matrix. So the fact that it's an inverse matrix, we write it as eta mu nu. Eta nu alpha is delta mu alpha. Matrix multiplication is sum of indices here. And the fact that it's an inverse means that the product is the identity matrix. Then the identity matrix here, maybe I should put the alpha here. This delta is as a matrix, is the matrix 1, 1, 1, 1. And zeros everywhere else. Yes?
So when we define the sign convention of the Minkowski matrix, do we define on ds squared or minus ds squared?
Right, that's yet another sign convention. So I put minus ds squared is equal to this, and that will be useful. So Books do it in different ways. It's your choice, and there are different conventions. But we put minus ds squared equal to this thing instead of ds squared. And the reason we do that is that we definitely want this metric to be minus plus plus plus. So this agrees with this. And the minus here is chosen in such a way that when you have a time-like interval, so a particle that doesn't move defines a time-like interval, then dx0 is positive, exists, the dx's are 0, say for a particle that doesn't move, and in that case, ds squared is positive. So in this convention, time-like intervals have positive ds squared, and that's convenient. So a couple of remarks here. Delta mu mu is sum over repeated indices is equal to d, is the dimension of space-time. In this case would be 4. Okay. Now, Lorentz transformations that we're going to use, we consider frames S and S prime with common origins. So both have this space-time point in common, or 0, 0. Which is to say they've adjusted their clocks and their axis in such a way that at some time that you can call 0 in both frames, the origins coincide. Now, after that, you can look at an event. Look at an event. P, described by coordinates x mu or coordinates x prime mu. And look at the interval, and what you should obtain then is that x0 squared, I don't know if I put this sign, yeah, I'll put minus x0 squared plus x1 squared plus x2 squared plus x3 squared is equal to minus x0, x prime 0 squared plus x prime 1 squared plus x prime 2 squared plus x prime 3 squared. Getting warmed up already, so this thing on the left-hand side and on the right-hand side are the intervals between that common origin and that point that you're looking at. And that's it. That's all you need to define Lorentz transformations. Lorentz transformations are linear transformations x mu to x prime mu that respect this formula that we call star. Now, you would say, well, do you want to say that, or you want to say linear invertible transformations that respect that? It's a small point, but it's an interesting point. Should I say linear invertible, or should I just say linear? Well, it's enough to say linear. You can try to construct a linear transformation that is not invertible, but you won't find a linear transformation that is not invertible that preserves this. And we'll see it right away. So how do we write this? We write this as x prime mu is equal L mu nu x nu. This is a matrix of numbers that transforms the x's into the x primes. The fact that this this equality should hold is star is the statement that eta mu nu x nu is equal to eta mu nu x prime mu x prime nu. So using that formula, it's eta mu nu L mu alpha L nu beta x alpha x beta. I used it twice. And then I relabel indices called mu and nu alpha and beta mu and nu in order to make this match. So you have eta alpha beta L alpha mu L beta nu x mu x nu. So far, so good. Now, the equality of these things, these two sides, actually means that these two things are the same. In general, it would mean that the symmetric part of this, because this is symmetric in mu and nu, is equal to the symmetric part of this, because this must hold for any x's. But this is symmetric by definition, and this is symmetric in mu and nu by construction. So it really means the equivalence of these two. So eta mu nu is equal to L alpha mu eta alpha beta L beta nu. And we write it as in matrix notation as eta is equal to. Well, here the matrix multiplication is not quite right. It's multiplying this index that is being summed is a row index as opposed to a column index. So what we need is to transpose here. So we get L transpose eta. And here the multiplication is fine, L. So L is a Lorentz transformation. Lorentz. If and only if it does that. We say it preserves the metric. It acts on a linear transformation acts on a matrix from the left and from the right. It's the natural thing. A linear transformation acts on a vector, but on a matrix itself, it has to act on the one index that is on the right, one index that is on the left, and that's how a matrix acts, and that's a Lorentz transformation. From where you get that the determinant of eta by the matrix property is equal to the determinant of L transpose times the determinant of eta times the determinant of L. Well, the determinant of eta is -1, but cancels from the two sides. And the determinant of L transpose is equal to the determinant of L. So this is squared. So the determinant of L must be either plus or -1. These are two types of Lorentz transformations. And any matrix with a determinant that is non-zero is invertible. So L invertible. So couple more things. We say that A mu is a vector if A prime mu if it transforms like the x's with a Lorentz transformation, then A is a vector. And then you define A mu to be eta mu nu A nu. You lower and raise indices with the eta matrix. As we keep on reviewing these basic things, I should say a couple more things about proper time. Proper time for a particle, say. We have minus ds squared is equal to, and you say you're sitting on a particle, and you put a Lorentz frame on that particle. In that Lorentz frame, there's only time going on because the frame is moving with the particle at least for a little interval of time. So this is minus dt on the particle. That's what is called a proper time squared and c squared. Remember the units have a c in there. And then if you look at it from the lab or from any other frame, it's minus c squared dt squared plus dx squared. If the particle in that frame has some velocity, this is minus c squared dt squared plus dx squared would be c v squared dt squared. So it's a rather simple thing how to calculate the proper time. You have in here minus c squared minus v squared dt squared. So the proper time is here. Now for a particle that is moving, this means that ds squared is equal to d tau squared times c squared, and you cancel the sign, and then we take the square root of this and we call it ds, is d tau times c. And so ds is defined to be the square root of ds squared. That sounds a little pedantic, but intervals are funny. ds squared may be positive, negative, or 0. So we write ds squared here, and we don't write minus ds squared. This is not what we mean here. We mean something called ds squared, and for good things like time-like intervals, this square root of ds squared is, you can take the square root and we call it ds. So if you have a vector, dx mu, ds is a relativistic scalar, so that's still a relativistic vector. And then it has no units, but it looks like a velocity, and it's clearly related to a velocity, at least in the spatial components, because ds is mostly c dt if the velocity is roughly small. So this is a relativistic velocity, and in order to have units of momentum, you put an mc. This has no units. And this is the relativistic momentum. It came out from there. It has a nice property, p mu is equal m squared c squared dx mu dx, I could put it mu down here, ds. In raising and lowering indices, this thing is really also dx mu, if I accept that we can raise and lower indices. So this thing is minus ds squared, so I get minus, this is minus 1, and I get minus m squared c squared, the opposite sign that Mark Weiss was doing this morning. The intervals notation, ds squared positive, we call it time-like. Ds squared 0, we call it light-like. And ds squared negative, we call it space-like. The intuition. You at the beginning of the class and you at the end of the class are defining a time-like interval, because ds squared is positive. And why is ds squared positive because you change the sign and you get dx0 squared minus all this. And a lot of time has passed, but you haven't moved that much. So you're definitely time-like. Light-like is what light does. If you consider two events joined by light, click a lantern, the beam reaches the moon, those two events are light-like separated. The amount of time is just right for the distance that the light travels. And these are two simultaneous events in one frame. So at 10 o'clock, this point and the point in the cafeteria are space-like separated. So one more piece of notation, A mu, B mu, the dot product. You can raise or lower indices A mu, B mu, and it's minus A0, B0, plus the sum from I equal 1 to 3 of AI, BI. So if you use both 0 and 0, the minus shows up. It's the minus of the eta here. So I could write it as eta mu nu, A mu, B nu. And you write it out and you get this. So these are basically all these things. Yes?
And why don't we call it the square of ds?
We don't want to call it the square of that because then if you had a space-like interval, suppose you have some interval in which this is 0, then this thing would all be positive. And if I call it the square of this thing, it would be imaginary, ds.
No, we don't want that.
Don't want that. Just not worth it. OK, now we're going to go this way. We go front, middle, middle. I'm not sure if I got it right, but anyway, good enough.
So maybe, can I ask you one question? So do you define this minus sign minus ds squared equals to eta mu dx mu dx?
Right, yeah.
That's very non-standard.
No, it's not very non-standard. I think Dirac does it, and there's several other relativists that do it. Yeah, it's sort of, it's the constraint that you want ds to be positive for a time-like interval, and you want eta to be minus plus plus plus. You're forced to that. It's not very non-standard, actually. In Misner, Thorne, and Wheeler, there is this appendix, or this last page, in which are all the conventions that people use in relativity. And there is that sign. That sign is part of the conventions. OK, I'm going to talk now about a set of coordinates that is a little less familiar, which is Lightcone coordinates. And they're defined by taking two of your coordinates, x0 and x1, and doing some change on that. Why do we do that? It's an incredible thing that actually, when you try to quantize the strength, it's extremely difficult to do it unless you choose Lightcone coordinates. Lightcone coordinates simplifies the physics and allows you to solve for all the constraints that the relativistic string has. The relativistic string is a constrained system. So Lightcone coordinates are very useful, and you need to understand a few things about them. x0 minus x1. You pick two of the coordinates, the time and another one, and form linear combinations. Now, if you have here x1 and x0, look at this point. This point at 45 degrees are the points on which x minus is equal to 0, because x0 is equal to x1. Therefore, the points x minus equal to 0 is called the axis x plus. Remember, the x-axis is the set of points where y is equal to 0. That's its definition. So this is the x plus axis, and this is the x minus axis. These are the points where x plus is equal to 0. Now, the issue is that even if we do Lightcone, we want to think of one of the Lightcone coordinates as time and the other as space. Now, what is the notion of time? What is the physical notion of time? It's the idea that if you have a particle that does physical motion, time increases. Time increases for physical motion. And physical motion are all these motions in which, say, motions with constant velocity are all these ones. These are physical motions. This here is not physical motion, you're going too fast. These are physical motion. For all of this, x plus and x minus increase. So, and it's very symmetric. So which you call time and which you call space is your choice. But make the choice once and never change it again. We call x plus time, Lightcone time. Now, what happens to your metric? It's an important thing. Well, from this equation, dx plus times dx minus times a 2. Dx plus times dx minus times a 2 cancels this thing and gives you dx0 squared minus dx1 squared. Therefore, minus ds squared is going to be equal to is minus dx0 squared plus this, so it's minus 2 dx plus dx minus, plus you still have the second coordinate and the third coordinate. I'll put one more equality here. This will be the Lightcone metric like this. I put a hat to distinguish that it's a Lightcone metric. And now the indices maybe should have hats or should use a different label, but I won't bother. What are the indices now run for? Before, mu and nu went from 0 to 3. Now they run. Mu can be a plus index, a minus index, 2, and 3. Because the 0 and 1 have been traded for plus and minus. So if you now try to write this eta mu nu metric, you have, and now it will have a plus, minus 2 and 3, and the other one here, x1, plus index, minus index, 2 and 3. Well, 2 and 3 is the same as before, so we have 1, 1, 0, 0. There's no mixtures between plus and minus and 2, 3 there, so this is big 0, big 0. The funny thing is how it all comes in the little matrix in here. In the little matrix in here, there's no plus plus, dx plus squared, no dx minus squared. So these are 0. And this is minus 1 and minus 1. So eta plus minus is equal to eta minus plus. It's symmetric after all, and it's minus 1. So let's go here. Now, here is a little exercise. Yes, please.
So what you're actually doing over here is nothing but just redefining just rotating it by 45 degrees, right?
But not really rigid rotation either.
I mean, you're choosing 2 out of your 4 coordinate, 2 out of your 4 coordinates, and all you're doing is just mixing it, linear combinations. So the rotation is just x naught sine theta plus y naught cos theta, and then you're just putting theta equals to 45.
Yeah, you could say we're doing exactly that. Yes.
So it is rigid rotation.
Yeah, no, it is a rigid rotation.
Yes.
I'm sorry, but it's not. Which is what I wanted to show, is that it's not a Lorentz transformation in the following sense. You see, and that's why I think I reacted immediately to your saying, no, it's not a rotation. In Lorentz transformations, you have boosts and you have rotations. But things that mix time and space are not usually called rotations. They're called boosts.
Yes. I mean, the coordinate frames will go like this. In place
That's
of going
right.
like this, they go nearby. Sure.
That's right. So it's not a rotation in the sense of Lorentz transformations, and it's not even a boost in the sense of Lorentz transformations. Because, as you said, it would do this kind of thing, and it's not done. So this is a little exercise. Show that the transformation x0, x1, x2, x3 goes to x0 prime, x1 prime, x2 prime, x3 prime equals to x plus, x minus, x2, x3 is not a Lorentz transformation. It's not a complicated exercise, but it's a good exercise. Make sure you understand why this is not a Lorentz transformation. Okay, more things on the Lightcone. For any vectors, you always define them like this: a0 plus minus a1. The dot product. Well, it would be eta mu nu hat. Now a mu, b nu, and this would be minus a plus b minus a minus b plus, and then the rest is standard. a2, b2 plus a3, b3. Remember, eta plus minus are pretty much the only things that exist, and they're -1 each, so you get these 2 terms there. Another curious thing, a minus is supposed to be eta minus mu, a mu. You're supposed to lower this sign, but the only thing that is non-vanishing once you have a minus in the eta is a plus. So this is eta minus plus a plus, and that's -1, so this is minus a plus. So it's kind of funny. A minus is minus a plus, and a plus down is minus a minus up. Yes?
The fact that this is not a Lorentz transformation just shows from the fact that it does not preserve the metric, right?
You could do it that way. And it also doesn't preserve the interval.
Yes.
And
if it doesn't preserve the metric, it does not preserve the interval.
Right.
Right.
And then, all right. One more thing. Lightcone velocity, it's sort of the Lightcone frame is sort of a non-relativistic frame. If you would say, OK, x plus is time, and x minus is space. So what is the Lightcone velocity? You would say maybe dx minus over dx plus measures the change in space with respect to time. And then you see there on this graph that I will redraw here, that if you're here, if you move like this, for example, here is x plus and here is x minus. In this limit, as you go in this direction, x minus doesn't change, but x plus does. So this goes to 0. So that Lightcone velocity is going to 0. In fact, a light beam going to the right here, x plus changes, but x minus doesn't. So it has 0 Lightcone velocity. V Lightcone equals 0. If you're not moving, dx minus, between any 2 points, dx minus is equal to dx plus, and the Lightcone velocity is 1. And if you're going in this direction, as you go in here, dx minus, if you go very close here, dx minus changes a lot, but dx plus changes very little. So the velocity is going to infinity. So here is Lightcone velocity equal infinity. So as you move from the Lightcone here, you got 0 velocity up to infinite velocity in that direction. It's sort of the peculiarities of the Lightcone that it looks like things are non-relativistic. Of course, nothing is non-relativistic, but the language is non-relativistic. One last comment is Lightcone energy. Here, this is the middle board, so that should go down. Now, one other thing I want you to understand is what is Lightcone energy. I will actually leave it up to you to look it up. Now, light energy, if you have the momentum for vector, is energy over c times the momentum like that. So the Lightcone, the energy that we usually call the energy is P0 times c, which is minus P0c. The Lightcone energy, or the energy expressing the Lightcone, you will discuss the analogy or read it in the book, is P plus C. So P plus C down is the Lightcone energy. Now, because of the Lightcone metric, you have here that this is P minus C. And this is the intuition that will be used all over in this course, that the Lightcone energy is P minus, up to a factor of C. But that's basically what we need. Now, the last thing I want to discuss in the last 5-6 minutes is making up spaces and compactification. It's a very useful tool in string theory that you can make up spaces by identifications, not by just any other kind of construction. Now, spaces that are made up by identifications are not extremely general, but they're general enough. So, for example, compactification and orbifolds. So, suppose I want to make a circle. I take the real line the x real line, and I make an identification. I say that P1 is identified with P2 if the coordinate of P1 and the coordinate of P2 differ by 2 pi r times any integer n that belongs to z. This is a funny way of describing a circle. This is saying, look, we'll identify these 2 points will be considered equivalent if their coordinates differ by a multiple of 2 pi r. So what do? You think about it, and you say, well, here's the origin, here's 2 pi r. Well, this point is the same as this point, is the same as this point, is the same as this point, but this point is the same as this one, because they differ by 2 pi r, is the same as that one. So if all these points are the same, you might as well consider a set of points, and that's it, with no identification. So you say, oh, let's consider this point from here to here. This point from here to here, there's no identification that says this point is equal to that. So these are genuine points, and they lead to what you would call the fundamental domain of the identification. Now, this identification, to save language, people write it as x similar x plus 2 pi r. They don't even write the n, because if x is equivalent to an x plus 2 pi r, then the second x is equivalent to another x plus 2 pi r, and you can do this ad infinitum. So even that n is not necessary. So this is the identification. And here you have something that is called the fundamental domain. Fundamental domain. What is a fundamental domain? Now we say, what is a fundamental domain? We don't say what is the fundamental domain, because there are many choices of fundamental domain, as you will see, but they're practical choices. A fundamental domain is a space such that, one, no 2 points are identified. And second, two, any point in the entire space, has a representative in the fundamental domain. So if I want to construct the fundamental domain here, I would say the fundamental domain is the set of points x between 0 and 2 pi r, and I put equal to 0 and less than 2 pi r, because any 2 points here inside cannot be identified, and since I have 0, I shouldn't have 2 pi r. So that's your fundamental domain. Now, oops. Okay. So now how do you build the space? The space that you're looking for is built by taking the fundamental domain, adding its boundary, and implementing the identification. So we take the fundamental domain, in this case is this. Now this fundamental domain is missing a boundary. Here the boundary at 0 is included, but the 2 pi r is not. So now you put x between 2 pi r and 0, and then implement the identification, which is to say now we have from 0 to 2 pi r, and we glue these 2 points, and we've made the circle. So we put the boundary, and we glue. I'm running out of time. I'll do a couple of small things, 2-3 minutes. A torus is done by this identification. xy similar to x plus 2 pi r y, and xy similar to x y plus 2 pi r. Why? Well, intuitively at least, in the xy plane, you say this identification moves any points 2 pi r and 2 pi r. So I go up to 2 pi r, and for the first identification, I would say, well, the fundamental domain is roughly this, because any point more, I can take it. But for the second identification, you have the same thing with here. So you can have here and another 2 pi r here. And now this is identified with this, with that. So at the end of the day, you really got this thing that seems to be a good fundamental domain. And it is a good fundamental domain, a square. And now these points are identified with this one. So this is with this. And these points are identified with that. And that's what we call a torus. We glue this, so you make a little cylinder, and then you glue the right end to the front end to the back end. You've got your torus. One exercise, and I'm quitting in 1 minute. Example, how about this thing? X plus 2 pi r, y plus 2 pi r. What is that in the plane? What do you say? Infinite what? You have to say it louder. Infinite.
So you can do from x from 0 to 2 pi r and y from 1 to 2.
Right.
And
So
also the other way.
So you can go here. You could say, well, x, this point here, and here is 2 pi r. This point is identified with this point. And then this identified with this, and this identified with this. So that's it. That's one presentation. But it's not very clear. There's one that is a little easier, that somebody there is doing with the hands.
Like a cylinder.
Sorry? It's some sort of cylinder, is that right? But here it's glued. This is glued with this is glued with that. So how do you describe it? You see, that's why a fundamental domain is the word. It's easier to describe it this way. So you take this line and you say, this point is identified with 2 pi r here, with this. So it's always the same thing. It's a vector that is at 45 degrees and has component x component 2 pi r and y component. So here is identified with this. So actually you have another line here with all separated by 2 pi r. And this line is glued nicely. So it's a cylinder with circumference, this thing, which is conference, square root of 2 times 2 pi r. So identifications are really fun things. We're going to do for tomorrow orbifold identifications, which are a little more exotic and take more time to figure out what they are. I thought I would cover it today, but it doesn't matter. We have plenty of time, and I will see you then tomorrow at 10:15.